Hello everyone, welcome to my YouTube channel. This is Enoch's tutorial. Don't forget to like and subscribe after watching the video so you can receive every update from this channel. In today's lesson, we are going to look at the solution to some past questions in the system, that is 2020-2021 Organic Chemistry past questions. We are going to first solve the first objective part, then also find solutions to the written part. Don't forget to like after watching so you can receive every update from this channel. So let's begin. Which of the following is 2-methyl 3-formal pentanoic acid? So among these options, which of them is 2-methyl 3-formal pentanoic acid? So the parent compound here is pentanoic acid. So let's see if you can identify pentanoic acid here. All the ones in the bracket here means that they are substituent. So here, this one is not pentanoic acid. This one is not pentanoic acid. This one shows that this compound is a pentanoic acid. And this one, we have 1 carbon here, 2, 3, so we have only 3 carbons, which is propanoic acid. So let's see here if this one matches the substituent formation here. We have 2 ethyl, so this is carbon 1, this is carbon 2, so this ethyl is on carbon 2. Then 3 formal, so this is formal group on carbon 3. So this is the answer, which is 2 ethyl 3-formal pentanoic acid. So question 1, the answer is D. Question 2, the effect of electron withdrawing groups on the carboxylic acid are that they. So what is the effect of electron withdrawing groups on carboxylic acids? 1, do they weaken acidity? No. Do they strengthen acidity? Yes. They stabilize themselves? No. They weaken? No. So the answer is they strengthen acidity and weaken basicity. So electron withdrawing groups like halogens and other oxygen derivatives, they pull electron from the carboxylate system to increase or to strengthen acidity of the carboxylic acids. So halogens and some other electron withdrawing compounds are the electron withdrawing groups. They tend to strengthen acidity of carboxylic acids. Question 3. Which reagents serve as the basis for simple chemical tests to distinguish between hexanoic acid and hexanamide? So we have which of these reagents can be used to distinguish between hexanoic acid, which is carboxylic acid, and an amide? Is it called dilute sodium hydroxide? No. Is it called concentrated sulfuric acid? No. Is it called sodium bicarbonate or what? Potassium permanganate. So the answer is B. When you treat carboxylic acid with sodium carbonate, you are going to evolve a carbon dioxide, which you can test by passing it through a lime water to form a milky substance. So when you treat carboxylic acid, each of these compounds with the sodium bicarbonate, you are going to evolve carbon dioxide, which can be tested by passing it through lime water, which turns it milky. So sodium bicarbonate can be used to distinguish between hexanoic acid and hexanamide, which is carboxylic acid and amide. Which of the following compound is not named so correctly, or is not named correctly? So let's look here. We have a isopropyl propanoate. So isopropyl propanoate, carboxylic acid portion is propanoate. Let's see. The alcohol portion is isopropyl, but here it is ethyl. So this one is wrong. This one is wrong. Tet-butyl acetate. So tet-butyl acetate. Okay, this one is correct. Methyl 2,2-dimethyl propanoate. This one is correct. Then 2,2-dimethyl butane-dioic acid. So this one is correct. So the answer, which is not correctly matched, is A. So the answer is A for the question 4. Now question 5. Which of the following is an amide? So among these set of questions or set of alternatives, which of them is an amide? An amide has nitrogen bonded to a carbonyl carbon. So here, this qualifies to be an amide. This is never an amide. This is an amine, and this is a diamine. So the answer is A. Question 5, the answer is A. This one is the only amide among this set of alternatives. It says arrange the following in order of increasing acidity. So we are to arrange these compounds in order of increasing acidity. So you have 2-methyl-butanoic acid, we have methyl, we have chlorine, we have bromine, and hydroxy. So among these four sets of substituent, which of them is electron withdrawing, which of them is electron donating, and which of them is stronger than the other? So you have hydroxy group, bromine, chlorine, and methyl. So the first place, the methyl is electron donating. So this one makes the I the weakest alternative. The I is the weakest of all. Then let's see the strongest. The hydroxy is the strongest of all. So the most acidic among these four is the IV, and the weak acidic among these four is the I. Then among bromine and chlorine, chlorine is more stronger in terms of electronegativity than bromine. So II becomes stronger acid than III. So the strongest acid is IV, followed by II, which is chlorine, then bromine, then methyl. So the correct answer is C. Forget about this one is wrong. The correct answer is C. Question 7. Which of the following compound is not an anhydride? So which of these is not an anhydride? A central oxygen bonding to carbonyl carbons defines an anhydride functional group. So this is an anhydride, this is 1, but C is not an anhydride. Question 8. Which of the following is cyclopentyl diethylamine? So cyclopentyl diethylamine. So let's see cyclopentyl diethylamine. The answer is B. This is cyclopentyl diethylamine. Question 9. Compound this gives a negative tolling test, but decolorize the solution of bromine. So if it gives a negative toluene test, then it means it is likely not to be an aldehyde or ketone. It is likely not to be an aldehyde or ketone. If it decolorizes a solution of bromine, it means it has some kind of unsaturation, double bond in them. When heated with sodium hydroxide, the fumes has a strong ammoniacal odor. So it means that the double bond is basically at the terminal. So here, let's see, it reacts with, it gives a negative toluene test, meaning that all the ones with nitrogen are out. Sorry, it is likely not to be an aldehyde or ketone. So among these ones, the ones that has a ketone or more of an aldehyde group are out. So this one makes this one qualify to be an answer. It's declaring solution of bromine water, so the C is out. So it is this. Then when heated with sodium hydroxide, the fume has a strong ammoniacal odor. So this one will give a negative toluene test. It will decolorize bromine in calcium tetrachloride, and it will give a fume of strong ammoniacal odor when treated or heated with sodium hydroxide because it has a terminal double bond. So the answer for question 9 is B. What is the product of the following reaction? So you have this reaction given you one. If you treat this compound with hydrogen cyanide, you will produce a dicyanide. So this CN will replace this. So you have this compound with 2 CNs. When you add hydrogen cyanide to this compound, then when you hydrolyze it in acid, you are going to get a dicarboxylic acid. You're going to have this compound as the final expected answer. So the answer is D. Which of these acids will undergo decarboxylation more readily? So decarboxylation produces a more stable resulting compound. So which of these will produce a more stable compound when they have been decarboxylated or carbon dioxide has been lost from them? The C and the D are the two challenging answers, but benzene become more stable when decarboxylated than cyclopentane? So the answer is D, because after decarboxylation of benzene, the resulting compound will be more stable than this one. So the answer is D. The A and B stands no way to be decarboxylated because they have no carboxylate functional group. Which of the following will readily be soluble in dilute aqueous solution? Aqueous HCl. So which of these will be soluble in dilute aqueous HCl? So all these are bases. So which of them is a strong base? This is how the question is trying to put. Because if it is a base, they will try to abstract a proton from an acid. So this one already exists in acidic form. This one already exists in acidic form. But among these compounds and aromatic amines, aliphatic amines are more basic than aromatic amines. So this one will be more soluble in a solution of aqueous HCl. So the answer is C. Which of the following statement is true about alkylation of amine? A. Alkylation of ammonia produces amine by nucleophilic addition reaction. Multiple alkylation can be minimized by using excess or large excess of ammonia. So this one is true. Tertiary amines can be synthesized using limited. No, this one is not true. The reduction of secondary amine using this one gives it. No, this one is not true. Got the first one, alkylation of ammonia produces amine by nuclear. No. So the correct answer, or the only true one among these four alternatives, is B. Next question. Select the best reagent and condition that can be used for the following transformation. So let's see if you have this benzaldehyde giving you this benzylamine, which possible transformation was adopted? This one is a possible oxidative amination done by not this, not this, not this, but it is this. So the answer is B. B is this one is the possible amine source which was used for the reductive amination of the benzaldehyde to produce oxidative amination of the benzaldehyde to produce this benzylamine. Question 5. Which of the following structures below is benzyl methylamine? So which of these is a benzyl methylamine? So this is benzyl methylamine. This one is correct. This one is wrong. This one is this one. The A and C are all the same, but the answer is this. So the answer is either A or C. I think there was a mistake. Benzyl methylamine can either be A or the C. I think there was a mistake because they are the same and they are all named benzyl methylamine. Now let's come to the section B, the written part. Okay, so we have to draw the product formed when cyclopentyl ethanoate react with water in the presence of acid. So cyclopentyl ethanoate is an ester. When it reacts with water in an acid, there's going to be hydrolysis to produce the corresponding ethanoic acid and the cyclopentanol. So let's see the solution. If there is a cyclopentyl ethanoate, when it is being hydrolyzed, we are going to produce the ethanoic acid and the cyclopentanol. So these two reactions, the reverse of this reaction is an esterification reaction, and the forward reaction is a hydrolysis reaction of ester to produce the corresponding carboxylic acid and the alcohol. Question 2. In the early 80s, the drug MPTR was sold as a synthetic heroin which caused irreversible symptoms of Parkinson's disease. The drug existed as a hydrochloride salt. Draw the salt. So if you have this as a drug with a tertiary amine functional group and you have to draw the hydrochloric salt of this, it is just by addition of the hydrochloric acid to this. When you add hydrochloric acid to this compound, it will produce a hydrochloric salt. where this one will pick one acid or one hydrogen from the acid, then surround itself with the ionic chlorine. So it is going to be like this. If that compound is treated with HCl, the N will pick the H from the HCl, then surround itself with a molecule of the negative chlorine ion. Question 3. Ethanoic acid and propanol have the same molecular weight, but the boiling point differ by 20 degrees. That is ethanoic acid is 118 and propanol is 97. Account for the difference. So what caused the difference? Basically, when ethanoic acid exists in a vapor state, it forms what we call a dimer. It exists in two molecular forms which are linked through hydrogen bonding. This tends to increase or double the molecular weight of the compound. So ethanoic acid in vapor state will have a doubled molecular weight than propanol. Therefore, will form a dimer. Therefore, will have a doubled molecular weight. So the ethanoic acid will form a dimer in the vapor state. Therefore, will have a doubled molecular weight. That accounts for the difference in boiling point between ethanoic acid and propanol, although they have the same molecular weight or similar molecular weight. Rank the following molecules in order of their relative reactivities. I think there's reactivities to a nucleophile in a nucleophilic ethyl substitution. Most reactive listed first. So let's see which of these is the most reactive form. We have this as derivatives of carboxylic acids. We have esters, we have anhydrides, we have ethyl chlorides and amides. Among all the derivatives, the most acidic or the most reactive one is the ethyl chloride. So this one is the most reactive one, then followed by the anhydride, followed by the ester, then finally the amide. So the amide is the most or the least reactive among this. So as we said earlier, it is the ethyl chloride first. The amide first, followed by the ester, the anhydride, and the ethyl chloride. Question 5. Write a structural formula for each of the following compounds. You have ethyl 3-oxobutanoate or ethyl acetoacetate. So this is the structure of ethyl. This is ethyl 3-oxobutanoate. So the ethyl here makes this one an ester. 3, here is carbon 1, here is carbon 2, this is carbon 3. So this is ethyl 3-oxo. Oxo is just a ketone group functioning as a substituent. We name that as an oxo. So ethyl 3-oxobutanoate. The next one is tetramethylammonium ion. So tetramethylammonium ion is this. There's a nitrogen of central or have four different methyl groups. Assuming a net positive charge is tetramethylammonium ion. Question 6. We have these transformations. We have an aniline with this reagent giving you A, we have B and C. Then you have to give the structure of the product A, B, and C in this sequence of the reactions here. Let's see how it goes. If you have an aniline and you add sodium nitrite and HCl, this one is more of you adding a nitrous acid to this. So it is an oxidation of amine. When you oxidize this, you are going to produce a diazonium ion. So this is the structure of A. This diazonium ion is not stable. This is A. Diazonium is not stable. When it is treated with copper cyanide, the cyanide ion will replace the whole of the ionic dinitrogen to form a benzonitrile. So this is a benzonitrile. When a benzonitrile is reduced with lithium aluminum hydride, so here it has double bonds in here, 3 double bonds in there. So this is A, this is B, this is B, and the C. So there was a mistake here. So the C looks like this. It has a benzonitrile and you reduce with a reducing agent lithium aluminum hydride. That reduces the double bond here to form a benzyl imine. So here it is no double bond. I'm coming. It is just going to be like this. It's just going to be this carbon bonded to the nitrogen with two hydrogens. So there's no triple bond here. It is just a carbon with a single bond to a nitrogens with two hydrogens. So this one, because the double bonds here, or the triple bond here, is going to be reduced by the lithium aluminum hydride. That finally gives you an amine. This is a synthesis of an amine from a cyanide. It is going to be C double bond C single bond N, then 2H. So C single bond N, 2H. This is benzyl amine. So here it is not a triple bond. It is a single bond from this carbon to this nitrogen and two hydrogens. Take note of that. So this one becomes the C. The next question, which is question 7, we are to give the IUPAC systematic or the common name of each of the following compounds. So this compound, how are you going to name it? As an ester, this one is going to be named as benzyl 2-methyl propanoate. So this one is benzyl 2-methyl propanoate. This is the benzyl 2-methyl. Is 2 because the methyl is on the second carbon of the propanoate. So benzyl 2-methyl propanoate, that's in here. Or it can also be named benzyl isobutanoate. Benzyl isobutanoate. Here to become it is cyclohexyl 2-methyl propanoate or cyclohexyl isobutanoate. That is for question 7. So it is, I think there was a mistake here too. It is benzyl 2-methyl propanoate, benzyl 2-methyl propanoate, and cyclohexyl 2-methyl propanoate, or benzyl isobutanoate, cyclohexyl isobutanoate. Here is 2 and not 3. Take note of that. Now let's go to section C. Section C says an alternative synthesis of ibuprofen is given below. We have to supply the structural formulas of compounds from A to D. So the first one is an acylation reaction. The second one is a reduction of the acyl group. The next one is another acylation reaction. And the next one is formation of cyanohydrin from an acylated benzene. So let's get the reactions here. We have the first one. This one is an acylation reaction where you add an acyl group. This is an acyl group. This compound is an acyl group. Without the chlorine, it's an acyl group. When you add this compound to this, you're going to have an acylated benzene. Then when it's reduced in 10HCl, you have a linear chain. When you acylate this again, you're going to have it at the para position. Then when you add sodium cyanide, you're going to produce a cyanohydrin. So this one, I think this one is A, this one is B, this one is C, and this one is D. The next question, you have to show how the following transformations can be achieved. So from this to this, the only change here is the conversion of the halide to a carboxylic acid. If you want to convert from halide to carboxylic acid, you first have to change this one to a Grignard reagent, then you carbonate it, or you can add sodium cyanide, then you hydrolyze it. So in the reaction, we have addition of magnesium in ether to produce a Grignard reagent. Then carbonation of the Grignard reagent gives you the final product. Or you can also go by this way. You can add sodium cyanide to this compound. So here you can add sodium cyanide to this compound to replace here with Cn. Then you add here just acid H3O plus, that is hydrolysis, to get the final product. So two mechanisms, either through addition of the magnesium in ether followed by carbonation, or you add sodium cyanide followed by hydrolysis, all gives you the final product. The next question, write equations for a simple chemical test that will distinguish between the following. We have an aniline and benzamide, and benzoic acid and aniline. So how are you going to do this? The first one is aniline and benzamide, benzoic acid and aniline. This one is an aniline, and which is a primary amine. So the test for an aniline in a compound, or let's say the test if a compound is an aniline, just have to add you have to go by what you call a carbyl-amine test. The carbyl-amine test is a test used to test for the presence of or primary and secondary amines in a compound. So as shown there, aniline is a primary amine. The test is just by addition of a hot solution or an alcoholic solution of potassium hydroxide in chloroform. Then that gives you a very foul smell isocyanide intermediate. This compound is an isocyanide intermediate which has a very foul smell. This shows that the compound there is a primary amine. So you have two tests, you have two compounds. You don't know which of them is an aniline, as in here, either the first one or the second one. You can go by the same test to test which of them is an aniline. You just add a solution of alcoholic, or let's say alcoholic potassium hydroxide in chloroform, and if you're able to detect or notice a foul smell compound, then that is an aniline. So it can be used to distinguish a solution or a mixture of aniline and benzamide, and also benzoic acid and aniline. That test can be used to distinguish between any of them. Taking these two, you can also go by this. For the second one, you can also go by not the carbyl-amine test. You can also go by addition of sodium carbonate to the benzoic acid, and that yields a carbon dioxide gas, which can be used to test that this compound is a benzoic acid. That is to say, whenever you add sodium carbonate to a carboxylic acid, the evolved gas is a carbon dioxide. We're going to see that in the next slide in the coming questions. Let's look at question 2a. It says butter yellow is a dye once used to color margarine. It has since been shown to be carcinogenic, and its use in food is no longer permitted. We have to outline the synthesis of the butter yellow from benzene and N,N-dimethyl aniline. So let's see how we can synthesize this compound. So this one is N,N-dimethyl aniline, and this one is the benzene. We are showing how we can synthesize the butter yellow from N,N-dimethyl aniline and benzene. First, we have to first nitrate the N,N-dimethyl aniline. So addition of a nitric acid in sulfuric acid, that positions a nitro group at the para position as seen here. HNO3 in H2SO4 positions a nitro group at the para position. Then when this one is reduced with hydrogen in palladium with a mild heat, you are going to reduce the nitro group to an ammonia or an amine group. So this is an amino group. So nitrated benzene can be converted to amine by reduction through this process. Now, having got the amine, you add a nitrous acid, which is formed from a reaction in sodium nitrite and HCl. That forms a diazonium ion. The diazonium ion can be treated with a benzene compound to form the butter yellow. I take it again. You first have to nitrate the benzene, and that put the nitro group at the para position here. Then you reduce the nitro group to an amino group. Then you add a nitrous acid, which is HNO2, formed from the reaction of sodium nitrite and HCl, and that forms a diazonium ion. On the component is a diazonium ion, and this one is not stable, hence it can be replaced. Now this one carries, or this benzene ring plus this, will replace, or this will bond this benzene ring to this compound. So addition of the benzene ring to the diazonium salt will link the benzene ring to this. So this benzene ring, this is the benzene ring, this is the benzene ring, and this is the added diazonium ion that we added. So this is how basically the beta yellow is synthesized. The next question, we are to devise a series of reactions to convert 1,1,3-dibromopropane to pentane 1,5-dioic acid, which is butyric acid. Let's see how we can synthesize that. It is 1,3-dibromopentane to pentane 1,5-dioic acid. So this is it. This is 1,3-dibromo pentane to pentane 1,5-dioic acid. So the first thing is to convert all this one. We have two reactions, two pathways for this reaction. We can first go by addition of 2 moles of sodium cyanide to replace the cyanide ions, or to replace the bromine ions with the cyanide here. So this will be replaced by cyanide, this one replaced by cyanide. Then after hydrolysis, it will be hydrolyzed to form carboxylic acid. Or in other way, you can also add magnesium in ether to form 2 moles of Grignard reagent. So you have a Grignard MgBr here and MgBr here. When you add 2 moles of magnesium in ether, then after you add carbon dioxide in acid, that is carbonation, that reduces or oxidizes the MgBr to carboxylic acid. So either the cyanide ion to carboxylic acid or magnesium to form a Grignard reagent to carboxylic acid. All two pathways works for converting 1,3-dibromopentane or dibromopropane to pentane 1,5-dioic acid. The next question, you have to write equations for simple chemical test again that will distinguish between this. So we have benzyl imine and benzanamide, ethanoic acid and ethyl imine. Let's see. So benzyl imine and benzylamide. This one is an imide, this one is an imine. So first, just test for the imine first using what we call a Hinsberg test. The Hinsberg test is treating the imine with a benzene sulfonyl chloride. This reagent is called a Hinsberg reagent. When you add this one to either primary or secondary amine, you're going to produce an intermediate which is not soluble in alkaline. So if you add benzene sulfonyl chloride to an amine, you produce a benzene sulfonamide, and that compound is not soluble in alkaline. So this test can be used to differentiate between amines and amide. So for the first one, you can use the Hinsberg test to test for the amine to produce this one. This compound, this benzene sulfonamide, is not soluble in alkaline. So after you reacting the amine with the benzene sulfonamide, then you test the resulting compound in an alkaline solution. If it is not soluble, it means that compound is the amine. So in between benzylamine and benzanamide, or ethanoic acid and ethylamine, all these two can be tested or can be differentiated using the Hinsberg test, which involves treating the benzylamine or the amine one with a benzene sulfonamide, benzene sulfonyl chloride, which is the Hinsberg reagent. Once again, the ethanoic acid can be tested by using, since the carboxylic acid, it can be tested by using a sodium carbonate or sodium bicarbonate. When you react sodium bicarbonate with every carboxylic acid, we are going to evolve a carbon dioxide, which is a gas that can be tested by passing it through a lime water to observe a milky substance. So either you use a benzene sulfonyl test for the II, or you use a sodium carbonate test. It works for any of them. Now 3a, when maleic acid is heated to 200 degrees Celsius, it loses water and becomes a maleic anhydride. Fumaric acid, which is a diastereomer of maleic acid, requires a much higher temperature before it dehydrates. when it does, it also yields the same malic anhydride. We have to provide a reason or explanation for this. This one is very simple. This is malic acid existing in a 6 geometric configuration, and this is fumaric acid existing in trans geometric configuration. In basic terms, the fumaric acid or the trans configurations are more stable and they form a very strong intramolecular hydrogen bonds, which makes them require much temperature for the dehydration. So it's because the fumaric acid has a stable trans geometric configuration, it will form a very strong intramolecular hydrogen bonding, which makes it require much heat to cause dehydration, hence making this one yield the malic acid at a very higher temperature. The active ingredient, so it was explained here. Let's see. So the fumaric acid is more stable and forms strong intramolecular hydrogen bond because it is in a trans configuration. Because it can form a very strong intramolecular hydrogen bonding, fumaric acid requires much temperature for its dehydration. The active ingredient of the insect repellent I can't see the word, but Genotox is N,N-dimethyl M-toluamide. What is this? We are to outline a synthesis of this compound starting with M-toluic acid. So this reaction can be more than 2 steps. We have this as the reagent, or let's say the repellent Genotox, and this is the starting material. So this one is very simple. We have to start from this. The reaction is very simple. First, you have to convert this carboxylic acid to an acyl chloride. Then you add this amine to form this amide. Here, this one is an amide. The functional group here is an amide. So first, convert this one to acyl chloride. Then you add an amine to form this amide. So let's see the sequence of reaction involved here. If you have this toluic acid, if you add thionyl chloride, you're going to produce an acyl chloride at this end, as seen here. Then this is the possible amine which you should add to get this compound. So adding this amine, this is a secondary amine. If you add this amine will, the nitrogen here will more of react with this carbon and displace this chlorine to form the final repellent. This is the answer. So this is a simple synthetic reaction which involves more than 2 steps, or this has just been 2 steps to get the final product. Now the last question here, we have to once again write an equations for simple chemical test that would distinguish between each of the following. So we have a cyclohexenamine and cyclohexane. So as we said earlier, if you have to differentiate between an amine, this one is an amine and alkene, you can use a Heisenberg test as we discussed in the previous slide. Treating this one with a benzene sulfonyl chloride will produce a phyl isocyanide intermediate. Or since this one is an amine and this one is an alkene, if you add this alkene to a bromine water, it will decolorize it, meaning that it's unsaturated. So with compounds, let's say 2 test tubes with this one and this one, testing which of them is cyclohexane and which of them is cyclohexenamine. Just add this one to bromine water, or just add bromine water to this compound, and if it decolorizes, no, it is brown color. If it decolorizes, then you say that this one, that test tube is the cyclohexane because it carries a double bond in there that causes decolorization of bromine water. The same way, butanoic acid and methyl butanoate, as we said earlier, here you can use a sodium bicarbonate or sodium carbonate to evolve a carbon dioxide to test for the presence of carboxylic acid in a compound. So there's a solution for that. If you add the cyclohexane to bromine water, which is bromine in carbon tetrachloride, it becomes decolorized. So this shows that that test tube or that compound is a cyclohexane because it carries a bond which can decolorize bromine water. But for the cyclohexenamine, it has no unsaturation in it. So even if you add bromine water to it, it can't cause any decolorization. It will still maintain the brown color for the bromine. If you are to use this one, the butanoic acid, this one is butanoic acid in sodium carbonate. The second one, butanoic acid in sodium carbonate. This is going between butanoic acid and methyl butanoate. Butanoic acid in sodium butanoate. We are going to produce sodium butanoate, as in here, water and carbon dioxide. So you have to test for butanoic acid. So we use sodium carbonate. Sodium carbonate reacting this one with butanoic acid will yield a sodium butanoate, water, and carbon dioxide. The carbon dioxide evolved can be tested by passing the evolved gas through lime water. So you can test that gas there is carbon dioxide because it turns a lime water milk because of the formation of calcium carbonate. Thanks for watching. Don't forget to subscribe after watching so that you can receive every update from this channel.